The lacewing enters the natural world without announcement. There is no sound to mark its arrival, no dramatic movement, no display of dominance. It drifts instead, light and deliberate, its fragile wings catching the air like thin sheets of glass. To an untrained eye, it appears harmless, almost ornamental, a fleeting presence that seems too delicate to matter. Yet beneath this appearance lies one of the most efficient and influential predators in terrestrial ecosystems, a species whose true power reveals itself not in adulthood, but in transformation. Lacewings belong to an ancient lineage of insects shaped by subtlety rather than force. Their evolutionary success is rooted not in strength or speed, but in timing, specialization, and invisibility. Long before human agriculture reshaped landscapes, lacewings were already embedded within food webs, regulating populations of smaller insects and stabilizing plant communities. They evolved not to dominate ecosystems, but to maintain them. The adult lacewing is defined by restraint. Its body is soft, slender, and light, colored in pale greens or muted browns that blend effortlessly into foliage. Its wings, transparent and intricately veined, are held roof-like over the body when at rest, creating the impression of a living leaf fragment suspended in air. These wings are not built for endurance or distance, but for controlled, precise flight within dense vegetation. The lacewing does not migrate across continents. It patrols micro-worlds. Its eyes, often golden or copper-toned, are highly sensitive to light, particularly at dusk and night. Lacewings are primarily nocturnal or crepuscular, active when the world quiets and visual predators retreat. This temporal niche reduces competition and predation, allowing lacewings to move through plant canopies with minimal interference. Their presence goes largely unnoticed, which is precisely the point. Feeding behavior in adult lacewings varies by species, but many consume nectar, pollen, and honeydew secreted by aphids. This diet provides energy for flight and reproduction, but it is not where the lacewing's ecological impact peaks. That impact begins earlier, hidden in the soil, on leaves, or beneath bark, long before wings ever form. The lacewing life cycle is a study in contrast. Eggs are laid individually, each perched at the end of a slender silken stalk attached to a leaf surface. This strange architecture is not decorative. It is defensive. By elevating eggs above the leaf, lacewings reduce the risk of cannibalism from newly hatched larvae and limit access by ground-based predators. Even before birth, survival is engineered. When the egg hatches, the transformation is immediate and unsettling. The lacewing larva bears almost no resemblance to the adult. Gone is the fragility. In its place emerges a compact, aggressive predator equipped with curved, hollow jaws designed to pierce and drain prey. This stage is where the lacewing reveals its true nature. Lacewing larvae are relentless hunters. They move with purpose across leaves and stems, responding to chemical traces and vibrations left by prey. Aphids, mites, thrips, whiteflies, and other soft-bodied insects are seized without hesitation. The larva injects digestive enzymes into its victim, liquefying internal tissues before consuming them. What remains is an empty husk, discarded without ceremony. This feeding strategy is not wasteful. It is efficient. A single lacewing larva can consume hundreds of pest insects over the course of its development. In agricultural and natural systems alike, this predatory pressure shapes population dynamics. Pest outbreaks are blunted, plant stress is reduced, entire trophic cascades are altered by a creature barely visible to the human eye. Behaviorally, lacewing larvae exhibit a level of adaptability uncommon among insects of their size. Some species actively camouflage themselves, collecting debris, insect remains, or plant material on specialized hooks along their backs. This living armor serves multiple functions: visual concealment, chemical masking, and physical protection. Predators searching for soft-bodied prey overlook what appears to be moving debris. This strategy speaks to the evolutionary environment in which lacewings emerged. Predation pressure was constant. Survival favored not only those who could hunt, but those who could avoid being hunted while doing so. The lacewing larva embodies this dual mastery. Habitat selection reflects this balance. Lacewings are found wherever plant life supports dense insect communities: forests, grasslands, wetlands, gardens, orchards, agricultural fields. They are not restricted to pristine environments. In fact, they often thrive at the boundary between natural and human-modified landscapes, exploiting pest species that flourish under monoculture conditions. This adaptability has allowed lacewings to persist through dramatic environmental shifts. Ice ages, climatic oscillations, habitat fragmentation, through all of it, lacewings endured by remaining functionally flexible. They do not depend on a single plant or prey species. They depend on imbalance. Where one insect population grows unchecked, lacewings follow. Yet this dependence on imbalance creates vulnerability in the modern world. Chemical pesticides do not discriminate. They eliminate prey and predator alike, collapsing the very systems lacewings evolved to regulate. Unlike pests, lacewings reproduce more slowly and invest heavily in each life stage. Recovery from chemical disturbance is therefore uneven, often favoring the species that cause damage rather than the ones that prevent it. Still, lacewings persist, drawn by light, guided by chemical signals, embedded deeply in ecosystems that rarely acknowledge them. Their story is not one of visibility, but of consequence. They operate below the threshold of human attention, yet their absence is felt immediately when pest populations explode and plants weaken under pressure. The lacewing does not announce its importance. It reveals it only when gone. The lacewing moves through the world almost unnoticed, a soft wing presence drifting through forests, fields, orchards, and gardens like a living fragment of air. Its wings, delicately veined and transparent, resemble fine lacework held together by biology rather than thread, and this fragile appearance has fooled humans for centuries. To the untrained eye, the lacewing looks ornamental, decorative, almost insignificant. In reality, it is one of the most quietly influential predators on land, a biological regulator whose impact ripples far beyond its size. Long before humans cultivated crops or divided landscapes into agriculture and wilderness, lacewings were already here. Fossil evidence suggests their lineage stretches back over 100 million years, emerging during a time when flowering plants were reshaping the planet. As ecosystems diversified, lacewings adapted with them, evolving not into brute force hunters, but into precision specialists. Their evolutionary success lies not in strength or speed, but in efficiency, adaptability, and an almost surgical approach to survival. The lacewing's body is light, slender, and deceptively simple. Most species are a soft green or pale brown, blending seamlessly into leaves and stems. Their compound eyes shimmer with a metallic gold or copper sheen, earning some species the nickname golden-eyed flies, though they are not flies at all. Their antennae extend forward like sensory instruments, constantly sampling the air for chemical cues that reveal food, danger, or opportunity. Every feature of the lacewing is tuned not for spectacle, but for function. Despite their ethereal look, lacewings are predators by design. As adults, many species feed on nectar, pollen, and honeydew, drawing energy from plants and aphid secretions. But the true power lies in their larval stage. Lacewing larvae are among the most efficient insect predators known, so effective that farmers and ecologists often refer to them as aphid lions. This is not poetic exaggeration. A single lacewing larva can consume hundreds of aphids during its development, exerting measurable control over pest populations without the use of chemicals or human intervention. The life of a lacewing begins quietly. Eggs are laid individually, each perched atop a slender, hair-like stalk attached to a leaf or stem. This strange structure is not decorative. It is a survival strategy. By suspending the egg away from the surface, the lacewing protects it from predators, cannibalistic siblings, and parasites. Even before hatching, the lacewing demonstrates a level of evolutionary foresight that reflects millions of years of selective pressure. When the larva emerges, the transformation is immediate and dramatic. Gone is the fragile elegance of the adult form. In its place appears a compact, armored hunter equipped with sickle-shaped mandibles designed to pierce, inject digestive enzymes, and drain prey from the inside. The larva does not chew its victims, it liquefies them. Aphids, mites, thrips, small caterpillars, few soft-bodied insects are safe once a lacewing larva enters the environment. Unlike many predators, lacewing larvae are solitary and intensely territorial. They do not cooperate, and they will not hesitate to attack other lacewing larvae if resources become scarce. Some species take this aggression a step further through a behavior known as debris carrying. These larvae camouflage themselves by covering their backs with the remains of their prey, aphid skins, plant fragments, dust, becoming mobile disguises that confuse predators and prey alike. This behavior blurs the line between organism and environment, turning the larva into a walking piece of its own ecosystem. Habitat flexibility is another cornerstone of lacewing success. They are found on every continent except Antarctica, occupying environments ranging from dense forests to arid grasslands, suburban gardens to industrial farmland. Their presence is closely tied to vegetation, not because they rely on plants directly for survival, but because plants host the insects they hunt. Where aphids thrive, lacewings are rarely far behind. This adaptability extends to climate as well. Lacewings can survive seasonal extremes by entering diapause, a state of suspended development that allows them to endure cold winters or dry periods. Some species overwinter as adults, hiding in bark crevices, leaf litter, or human structures. Others overwinter as pupae, sealed within silken cocoons spun during the final larval stage. These strategies allow lacewings to persist across years, re-emerging when conditions again favor life and reproduction. Reproduction in lacewings is guided as much by chemistry as by behavior. Adults rely heavily on pheromones to locate mates, and even subtle changes in environmental conditions can influence mating success. Once fertilized, females carefully select egg-laying sites, often choosing leaves already infested with prey insects. This ensures that when larvae hatch, food is immediately available, reducing the risk of starvation and increasing survival rates. The lacewing's role in ecosystems extends far beyond simple predation. By regulating populations of herbivorous insects, lacewings indirectly protect plants from overconsumption. This stabilizing effect cascades upward through the food web, influencing plant health, soil quality, and even the abundance of other insect species. In agricultural systems, lacewings act as unpaid laborers, reducing the need for pesticides and helping maintain ecological balance. Yet despite their importance, lacewings remain vulnerable. Habitat loss, pesticide use, and monoculture farming practices have reduced their numbers in many regions. Chemical insecticides, in particular, pose a significant threat. Lacewings are sensitive to toxins designed to kill pests, and large-scale spraying can wipe out local populations, removing a natural line of defense against future infestations. Ironically, the elimination of lacewings often leads to pest outbreaks that require even more chemical intervention, creating a destructive feedback loop. Humans are only beginning to fully appreciate the lacewing's value. In recent decades, biological control programs have intentionally introduced lacewings into agricultural systems, recognizing their ability to manage pests sustainably. These efforts reflect a broader shift in thinking, one that views ecosystems not as systems to dominate, but as networks to understand and support. The lacewing does not announce its presence with noise or color. It does not build monuments or command attention. Its power lies in subtlety, in the quiet repetition of predation, reproduction, and survival across generations. It is a reminder that influence in nature is not always visible, and that some of the most important forces shaping the world operate on wings so thin they are almost invisible. As the lacewing matures beyond its larval stage, its transformation is not merely physical but ecological. The transition from voracious ground-level predator to airborne adult marks a shift in role rather than a reduction in importance. Where the larva dominates through direct consumption, the adult lacewing influences ecosystems through movement, reproduction, and chemical interaction with its environment. This dual-phase strategy is one of the reasons lacewings have endured while countless other insect lineages vanished. The adult lacewing's flight is slow, drifting, almost hesitant. Unlike fast-flying insects that rely on speed to escape danger, lacewings depend on camouflage and timing. The green coloration blends into foliage so effectively that they often disappear mid-flight when they land on a leaf. This visual invisibility is reinforced by behavioral subtlety. Lacewings are primarily nocturnal or crepuscular, becoming most active during dusk and night when predators are fewer and humidity levels favor survival. At night, lacewings navigate using a combination of visual cues and chemical signals. Their eyes, though not adapted for sharp image resolution, are highly sensitive to low light and motion. More importantly, their antennae function as advanced chemical sensors, detecting pheromones released by other lacewings as well as volatile compounds emitted by plants under insect attack. When aphids feed on a plant, the plant releases distress chemicals into the air. Lacewings have evolved to recognize these signals, effectively allowing them to hear a plant calling for help. This plant-insect communication places lacewings at the center of a hidden network that connects flora and fauna. They do not simply wander randomly in search of food or mates. Their movements are guided by invisible chemical trails that map the health of entire landscapes. In this way, lacewings act less like individual animals and more like mobile sensors, responding dynamically to ecological imbalance. Feeding behavior in adult lacewings varies by species, but it is always strategic. Nectar and pollen provide energy for flight and reproduction, while honeydew, sugary waste produced by aphids, serves as a bridge between plant-based and predatory lifestyles. By feeding near aphid colonies, adult lacewings increase the likelihood that their offspring will encounter abundant prey. This tight coupling between adult feeding choices and larval survival reflects a level of evolutionary integration rarely appreciated in insects. Social structure among lacewings is minimal but not non-existent. They do not form colonies or swarms, yet their populations are loosely synchronized through environmental cues. Seasonal changes in temperature, day length, and food availability trigger coordinated emergence, mating, and egg-laying across wide areas. This synchronization ensures that larvae appear when prey populations are rising, maximizing their impact and survival. Mating itself is a precise and vulnerable process. Lacewings rely heavily on pheromones, and even slight disruptions, air pollution, pesticide residues, or habitat fragmentation, can interfere with chemical communication. Males locate females by following faint scent gradients through the air, a process that demands stable atmospheric conditions. Once mating occurs, the female's focus shifts almost entirely to reproduction strategy, not quantity alone, but placement and timing. Egg placement is one of the lacewing's most remarkable behaviors. Each egg is mounted on a slender stalk, often several millimeters long, lifting it away from the leaf surface. This adaptation serves multiple purposes at once. It reduces the risk of predation by ants and beetles, limits fungal infection in humid conditions, and prevents newly hatched larvae from immediately attacking each other. In environments where food is scarce, this separation can mean the difference between a functioning predator population and complete collapse through cannibalism. When larvae hatch, the ecosystem feels their presence almost immediately. Aphid populations decline, plant stress decreases, and the balance between herbivores and vegetation begins to shift. This effect is not localized to a single plant. Because lacewing larvae are mobile, they move between leaves and stems, spreading their influence across entire fields or forest industries. Their predation is relentless but not wasteful. They consume only what they need, leaving enough prey for continued ecological function. One of the most unsettling yet fascinating aspects of lacewing larvae is their method of feeding. Using hollow mandibles, they inject digestive enzymes into their prey, dissolving internal tissues before extracting the liquefied contents. This external digestion allows them to process prey larger than themselves and minimizes handling time, reducing exposure to predators. It is a strategy optimized for efficiency, honed by millions of years of selection. Predators of lacewings do exist, despite their camouflage and chemical defenses. Birds, spiders, ants, and larger insects all prey on lacewings at various life stages. To counter this, lacewings rely on a layered defense system: visual camouflage, nocturnal activity, debris-carrying larvae, and in some species, the release of foul-smelling defensive chemicals, combine to create a survival strategy that is probabilistic rather than absolute. Lacewings do not aim to be invincible, they aim to survive long enough to reproduce. Environmental pressures have shaped lacewing populations differently across regions. In stable, biodiverse habitats, lacewings tend to exhibit slower development and longer lifespans. In disturbed or agricultural environments, rapid development and high reproductive output are favored. This plasticity allows lacewings to persist even as humans radically alter landscapes. However, it also masks their vulnerability. Populations may appear stable until a critical threshold is crossed, after which recovery becomes difficult. Modern agriculture presents both opportunity and danger for lacewings. Fields rich in pest insects can support large lacewing populations, but chemical pesticides often eliminate them before they can exert control. Even sublevel exposure can disrupt reproduction, navigation, and larval development. The decline of lacewings in heavily treated areas often precedes outbreaks of resistant pest species, illustrating their role as an early warning indicator of ecological imbalance. Beyond agriculture, lacewings contribute to natural ecosystems in quieter ways. By regulating insect populations, they influence plant diversity, which in turn affects pollinators, herbivores, and soil organisms. Their impact is diffuse but cumulative, shaping ecosystems over time rather than through dramatic events. In this sense, lacewings embody a fundamental principle of ecology. Stability emerges not from dominance, but from balance. As human awareness of ecological complexity grows, lacewings are increasingly recognized not as minor insects, but as keystone participants in terrestrial systems. Their presence signals resilience, adaptability, and functional diversity. Their absence, though often unnoticed, leaves a vacuum that no chemical or mechanical substitute can fully replace. The relationship between lacewings and their environment is not static, it is a continuous negotiation shaped by change, disturbance, and adaptation. As landscapes transform, through climate shifts, urban expansion, and agricultural intensification, lacewings respond not with resistance, but with recalibration. Their survival strategy is not to dominate a niche permanently, but to move fluidly between opportunities as they arise. Climate change has introduced new pressures into this balance. Rising temperatures accelerate lacewing development, shortening life cycles and increasing the number of generations produced each year in some regions. On the surface, this appears advantageous. More generations mean more predators and greater pest control. Yet this acceleration comes at a cost. Rapid development can reduce body size, weaken immune defenses, and desynchronize lacewing life cycles from those of their prey. When timing drifts out of alignment, even efficient predators struggle. Humidity also plays a critical role in lacewing survival. Eggs and larvae are particularly sensitive to moisture levels. Prolonged drought can desiccate eggs before hatching, while excessive humidity encourages fungal growth that attacks larvae and pupae. In natural ecosystems, these extremes are buffered by vegetation diversity and microhabitats. In simplified landscapes, such as monoculture farms, lacewings face environmental volatility with fewer refuges. Urban environments present a different challenge. Cities fragment habitats into isolated patches of greenery separated by concrete and glass. Surprisingly, lacewings often persist in these spaces. Gardens, parks, green roofs, and even roadside vegetation can support lacewing populations if prey insects are present. Artificial lighting, however, disrupts the nocturnal behavior, drawing adults away from optimal breeding sites and increasing predation risk. The modern city becomes both refuge and trap. The lacewing's interaction with humans is largely unintentional, yet deeply consequential. For centuries, lacewings existed alongside agriculture without recognition. Only with the rise of industrial pesticides did their absence become noticeable. Fields once balanced by natural predators became dependent on chemical inputs, and pest populations evolved resistance at alarming rates. Lacewings, once eliminated, were difficult to reintroduce without addressing the underlying ecological simplification. This realization sparked a shift toward integrated pest management, a strategy that seeks to work with natural systems rather than against them. Lacewings became symbols of this approach. Their ability to suppress pests without harming crops or beneficial insects made them ideal allies. Commercial breeding programs began producing lacewing eggs and larvae for release into fields, orchards, and greenhouses. In these controlled introductions, lacewings demonstrated their value repeatedly, often outperforming chemical treatments over time. Yet even these efforts revealed limitations. Lacewings cannot function in ecological isolation. Without flowering plants to provide nectar, without shelter from weather extremes, and without a diversity of prey, introduced populations fail to establish. Their success depends not on presence alone, but on context. This dependency highlights a broader truth: biological solutions require biological complexity. Predation pressure also shapes lacewing behavior in subtle ways. In environments with high bird density, adult lacewings reduce daytime activity and shift flight patterns to remain within vegetation cover. In areas dominated by ants, larvae increase debris-carrying behavior, masking their scent and appearance. These adjustments are not learned in the human sense, but encoded through generations of selection. Each individual lacewing carries a compressed history of survival strategies refined over evolutionary time. The pupal stage marks another critical transition. After completing larval development, the lacewing spins a silken cocoon, often hidden among leaves or soil debris. Inside, the larval body dissolves and reorganizes, a complete biological reconstruction. This process is vulnerable to disturbance. Mechanical tilling, heavy rainfall, or trampling can destroy cocoons before adults emerge. In natural systems, this loss is absorbed by population redundancy. In managed systems, it can collapse entire cohorts. Emerging adults face a narrow window to feed, mate, and reproduce. Their lifespan is relatively short, measured in weeks rather than months. This brevity intensifies selective pressure. Every successful mating, every correctly placed egg, carries disproportionate weight in determining the future of the population. Lacewings do not rely on longevity, they rely on precision. Their influence extends beyond insects. By protecting plants from herbivorous pressure, lacewings indirectly support pollinators, seed dispersers, and soil organisms. Healthier plants mean stronger root systems, improved soil structure, and greater carbon retention. These effects accumulate slowly, almost invisibly, but over time they shape ecosystem resilience. In this way, the lacewing's impact reaches into processes that operate on far larger scales than the insect itself. There is also a psychological dimension to the lacewing story. Humans tend to value animals that are large, charismatic, or emotionally expressive. Lacewings offer none of these qualities. They are small, silent, and easily overlooked. Yet their importance challenges this bias, reminding us that ecological value is not correlated with visibility. The most critical actors are often those that operate unnoticed. Scientific research continues to uncover new layers of lacewing biology. Studies on their sensory systems reveal unexpected sophistication, particularly in chemical detection. Genetic research shows high adaptability within populations, suggesting resilience to moderate environmental change. However, this resilience is not infinite. There are thresholds beyond which recovery becomes unlikely, especially when habitat loss and chemical exposure combine. The lacewing's future, therefore, is intertwined with human choices. Conservation does not require grand gestures or protected reserves alone. It can begin in gardens, farms, and managed landscapes by reducing pesticide use, planting diverse vegetation, and allowing small pockets of wildness to persist. Where lacewings are given space, they respond quickly, re-establishing the quiet functions they have performed for millions of years. In the broader narrative of life on Earth, lacewings occupy a paradoxical position. They are ancient yet adaptable, fragile yet powerful, invisible yet essential. Their story is not one of dominance or conquest, but a balance maintained through countless small actions repeated across time. In a world increasingly shaped by human hands, this form of influence may be the most important of all. When the lacewing story is viewed across geological time, its greatest strength becomes clear: continuity. While continents shifted, climates oscillated, and mass extinctions erased dominant lineages, lacewings persisted by never placing all evolutionary weight on a single strategy. They survived not by becoming larger, faster, or more aggressive, but by refining efficiency at every scale of their existence. This quiet persistence defines their place in the living world. The lacewing does not alter landscapes directly, yet landscapes change in response to its presence. By keeping herbivorous insects in check, it prevents population explosions that would otherwise strip vegetation and destabilize ecosystems. This control is not absolute and not constant, but adaptive. Lacewings respond to abundance with reproduction, to scarcity with restraint. Their populations rise and fall in rhythm with the systems they inhabit, reinforcing equilibrium rather than disrupting it. Over evolutionary time, this role has shaped not only prey species but plants themselves. Plants that host aphids and other herbivores benefit indirectly from lacewing predation, experiencing reduced stress and increased reproductive success. In turn, these plants continue producing the chemical signals that attract lacewings, strengthening a feedback loop that binds species together across trophic levels. The lacewing exists within this loop as both participant and regulator. Modern science increasingly frames lacewings as indicators of ecological health. Their presence suggests functional complexity, diverse plant life, stable insect communities, and minimal chemical disturbance. Their absence often signals imbalance, simplification, or environmental stress. In this way, lacewings act as biological diagnostics, revealing truths about ecosystems that may not yet be visible through plant decline or soil degradation. Despite this, lacewings face an uncertain future. Global insect populations are declining at alarming rates, driven by habitat destruction, pollution, climate instability, and intensive land use. Lacewings are not immune. While their adaptability offers some protection, it cannot compensate indefinitely for the loss of suitable habitat and chemical safety. Evolution equipped species to respond to gradual change, not rapid, systemic disruption. There is a quiet irony in the lacewing's relationship with humanity. We depend on the ecological services it provides, yet rarely acknowledge its existence. We invest in technologies to replicate what lacewings do naturally, often at great cost and with unintended consequences. The lacewing asks for nothing beyond the conditions it evolved within: plants, prey, and time. In recent years, awareness has begun to shift. Gardeners plant flowering species to attract beneficial insects. Farmers experiment with reduced chemical inputs. Urban planners incorporate green spaces into city design. In these small decisions, lacewings find opportunity. Their return is often swift, their impact subtle but measurable. Where they reappear, ecosystems begin to regain their self-regulating capacity. The lacewing's fragility is not weakness. It is precision. Thin wings reduce energy costs. A light body allows efficient flight. Specialized larvae maximize predatory output with minimal waste. Every aspect of the lacewing reflects optimization rather than excess. In an era defined by overconsumption and escalation, this strategy offers a powerful counterexample. From a human perspective, lacewings challenge how value is assigned in nature. They lack charisma, size, and spectacle, yet their contribution rivals that of far more celebrated animals. They remind us that ecosystems are not maintained by icons alone, but by countless small agents performing essential tasks without recognition. As night falls and lacewings take to the air, their movements leave no trace. No sound marks their passage. No visible change announces their work. And yet, by morning, aphid numbers are lower, leaves show less damage, and plants stand stronger. This is the lacewing's legacy: influence without attention, power without dominance. In the long arc of life on Earth, the lacewing stands as proof that survival does not require visibility, only effectiveness. It survives not because it is noticed, but because it works. And as long as ecosystems endure, quietly balancing themselves through countless interactions, the lacewing will remain among their most faithful guardians.